topic of today's video is area between the curves. From Calc 1, remember, the integral represents the area between f of x and the x-axis, and any area below the x-axis is negative. So area between the curve f of x and the x-axis is the positive area. Area below the x-axis is negative area. So the area under the curve, in Calc 1, we figured out area under the curve. That's integral from a to b f of x dx, where a and b are the x coordinates. How do we find area between two curves? To find the area between two curves, we can, first we need to think about, are we given y as a function of x or x as a function of y? First, we're going to look at examples where y is a function of x. Okay, so y is a function of x. In the first few examples, y is a function of x. So here we're given two curves in the graph. We have a top curve and a bottom curve, and we want to find area between the curves. So let's go back and think about, if I perform the integration of f of x, integral of f of x dx from a to b, I'll get all of this area. And if I find a to b g of x dx, I'll find this much area. And if I subtract these two integrals, then I will get the area between the two curves, which is going to be the shaded area here. So that's what we would be doing now. If f of x is greater than or equal to g of x on the interval ab, the formula for area between the curves is a to b f of x minus g of x dx. Keep in mind, you have to do top curve minus the bottom curve, because top curve will have the bigger area beneath it. So first we need to figure out which one is a top curve, which one is a bottom curve. Graphing can help us out. If you don't want to graph, you can also plug different x coordinates to see which one gives you higher y values. That would be okay to find out which curve is on the top, which curve is on the bottom. The next thing we need is point of intersection of those two curves. So we want to find out, where do the two curves intersect? Those will be our bounds of integration, wherever the two curves intersect, unless we are given interval, x interval in the problem where we are looking for area between the curves. So what happens if one curve is above x-axis and one curve is below x-axis? So if both curves are above x-axis, like in this example, the area between the curves will be some positive area. So we're going to do the top curve area minus the bottom curve area. But if one curve is above, one curve is below, when we do top curve area minus the negative area, which is area below the x-axis, those areas will add up. So you will still get some positive area. Steps to find area between the curves. The first step is sketch the graph, if anything, just to see what it looks like. This step can be skipped. If you don't know how to graph, you take help from Desmos. Some functions are very tedious to graph by hand, so you can take help of Desmos, and that's a free graphing calculator. Identify the top and bottom curve. Graph will help us identify that. Again, if you did not graph, then just plug different x values to see which curve gives you higher y value. That will be your top curve. If the curves switch out, that means the top curve becomes bottom curve becomes top curve, then we'll have to separate the integrals. Find the limits of integration. To find limits of integration, we will have to plug the curves equal to each other. Set the two curves equal to each other and solve that equation, and that's going to give us bounds of our integration. Set up the integral and evaluate. Integral a equal to a to b top function minus the bottom function dx. When y is a function of x, we will integrate with respect to x, so we'll have dx in our integral, and the a and b will be the x values. On the other hand, little later we'll talk about when x is a function of y, then the a and b will be the y values, and instead of dx we will have the dy. Okay, let's look at some examples. Here's the first one. Find the area between the curves f of x equals x squared minus 4 and g of x is x plus 2. So area between the curves is all this area. Go ahead and graph them first to see which curve is on the top and which curve is on the bottom. Once you have the graph, we want to figure out the points of intersection. To find the points of intersection, set the two curves equal to each other. And once we solve that equation for x, we would be able to tell where do the curves intersect. What x coordinates are the points where the curves intersect. So x squared minus 4 equals x plus 2. This will leave me with x squared minus x minus 6 equal to 0. Two numbers multiply to give you negative 6. So I get x as negative 2 and positive 3. So negative 2 and positive 3. So now I want to find out what are exact coordinates. So I'm going to plug x as negative 2 in any of those, in any equation. If I plug x as negative 2, y comes out to be 0. So here are my points of intersection, negative 2, 0. You don't need the y coordinates, but it's just helpful to think about where are your exact points of intersection. You only need the x coordinates, and you don't have to find the y coordinates. So if I plug x as negative 2, x as 3 in here, 3 squared is 9 minus 4, I get 5. So for 3, 5, these are my 2 points of intersection. Again, we only need the x coordinates, we don't need the y coordinates. Let's go ahead and set up the integral. My top curve is g of x, the bottom curve is f of x. So starting the point bounds of integration are the points of intersection. The top curve in this case is g of x, bottom curve is f of x dx. And that's going to leave me with g of x is x plus 2 minus f of x is x squared minus 4 dx. So between negative 2 to 3, x plus 2 minus x squared plus 4 dx. Now this is definite integral. I will be using an integral calculator. My goal in this course is not to, I'm assuming that you are very good at evaluating definite integrals. So that's not what I want to spend time on here. So negative x squared plus x plus 6 dx. Now to evaluate this integral, we can go ahead and isolate these. So when I perform the integration, negative x cubed over 3 plus x squared over 2 plus 6x between negative 2 to 3. Now I'm going to use a calculator to perform the integration, and let's see, what does it turn out to be? So I get 125 over 6, and that's the area between these two curves. Let's see several more examples. Determine the area bounded by two functions. Again, we have y as a function of x. So our two graphs are trig graphs here, sine x and cosine x. You should know by heart how to draw sine x and cosine x. Sine x starts at 0, ends at 0, from 0 to 2 pi. And cosine x, I'm just going to mark this point as 2 pi. For cosine x, it starts at 1 and ends at 1. And they toggle between 1 and negative 1. So I need to figure out which one is a top curve, which one is a bottom curve, and we want to find the area in this interval. We are given the interval from pi over 4 to 5 pi over 4. So from pi over 4 to 5 pi over 4, let's go ahead and check where is the pi over 4. Sine and cosine are equal at pi over 4. So they have the same value at pi over 4. Maybe I shouldn't make it, a dark line. I just wanted to mention that this is where pi over 4 is. So we're trying to figure out the area between the curves from pi over 4 to pi over 4. And this point is where we have pi over 4, and this is where we have 5 pi over 4. All right, so let's see. The top curve looks like is sine of x here. The bottom curve is cosine of x. So perform the integration. The points of intersection are pi over 4 and 5 pi over 4. If we were not given the points of intersection, we would set the two curves equal to each other and solve them. And we would be able to see both of them have the same positive y value at pi over 4, same negative y value at 5 pi over 4. So pi over 4 to 5 pi over 4, sine x minus cosine x dx. Okay, we can isolate the two integrals. Sine x integral is negative cosine x, and integral of cos x is sine x, and the bounds are pi over 4 to 5 pi over 4. So negative cosine pi over 4, negative cosine 5 pi over 4 minus sine pi over 4, sine 5 pi over 4, minus, it would be plus cosine pi over 4, and when I distribute the negative, it would become plus sine pi over 4. And grab a calculator. Make sure you're always in the radian mode. In calculus, we would never use the degree mode. So we would get root 2 over 2 minus, and that would be a plus root 2 over 2 plus root 2 over 2 plus root 2 over 2. And that would turn out to be 4 root 2 over 2, which is going to be 2 root 2. So that's what our area between the curves is going to be, 2 root 2, because we can simplify here. So 2 root 2 is the area between the curves. Another example, find the area between the curves. F of x is x squared minus 5x minus 7. G of x is x minus 12. And we are given the interval between -2 to 5. So we're going to have to focus on this interval now, not just where the curves intersect. Okay, so if you draw this graph and you see my f of x curve is my parabola, g of x is a straight line, and I am looking for between -2 to 5. So I have multiple regions here. So I have to find this region. This is the area between the curves. And then I also have to find the green and the pink region. Those are the areas between the curves. So I need to figure out where do the two curves intersect. So curves intersect at what point? Curves intersect at x squared minus 5x minus 7 equals x minus 12. X squared, subtract the x, that's -6x. Add 12 plus 5 equal to 0. X minus 5, x minus 1 equal to 0. X equals 1 and 5. So this is 1, and this is probably 5, wherever they intersect. So now I'm ready to write. I will have to separate the two integrals, because in some region I have the parabola on the top and the line is on the bottom, and some other region, in the green region, I have the line on the top and parabola on the bottom. So two separate integrals. We'll have to separate because your top curve and the bottom curve are changing here. So I'm going to have to go ahead and do -2 to 1. Between -2 to 1, my top curve is a parabola, which is x squared minus 5x minus 7. And my bottom curve is the line, which is x minus 12 dx, plus between 1 to 5, my top curve is the line, x minus 12, and the bottom curve is x squared minus 5x minus 7 dx. So let's go ahead and evaluate this in these two integrals now and see what we are, what does it turn out to be between -1 to 2. Between -1 to 2, I would have x squared minus 6x plus 5, x squared minus 6x, x squared minus 6x plus 5. Okay, so x squared minus 6x plus 5 dx plus, and now I'm going from 1 to 5. 1 to 5, I have x, negative x squared plus 6x, negative x squared plus 6x, and then I would have a -12 plus 7, which is going to be minus 5 dx. So here's my two integrals, and I need to go ahead and evaluate them, simplify them, and I'm just going to use a calculator here. I'm not going to bother to do them, evaluate them individually. Let me just double check and make sure that I do have x squared minus 6x plus 5, right? And then negative x squared plus 6x minus 5, right? So definite integral, my bounds are -1, -1 to 2, okay, x squared minus 6x turns out to be 113 divided by 3. So again, feel free to use a calculator to perform the definite integral. There's no need to do it manually. It would be just time consuming. Here we have next example. That was the example number 4. We have to find the area between the curves f of x equals e to the power x and g of x equals e to the power 2x. And we're looking for over the interval 0 to 1. So e to the power x would be a lower curve, e to the power 2x. Exponential functions, as your exponent gets bigger and bigger, they rise very, very quickly. They rise sharply as your exponent is getting bigger and bigger. So I am ready to set up this integral. I already know my top curve and the bottom curve, and I don't have to worry about points of intersection because I'm already looking between 0 and 1. They do intersect at 0, but beyond that, they never intersect. So if I was not given the interval, then I wouldn't be able to figure out the area between the curves because there would be infinite area. So going from 0 to 1, the top curve is e to the power 2x minus the bottom curve is e to the power x dx. Now let's perform the integration and see what does it turn out to be. For e to the power 2x, it would be e to the power 2x divided by 2 minus e to the power x, and the bounds are 0 to 1. Once we perform the integration, let's go ahead and plug a 1 in there and then a 0. E to the power 2 times 1 is 2 over 2 minus e to the power 1 minus e to the power 2 times 0 is 0 over 2 minus e to the power 0. Okay, so that looks like it would be e to the second power over 2 minus e minus 1/2 minus 1. E to the power 0, any number to the power 0 is 1. Keep that in mind. So that would be e to the power 2 minus e negative 3/2, negative 1/2. It would be plus 1 here when we distribute. So that's going to change. That would be 1 minus half. That would be plus 1/2. And that's all. And that's the area between the curves. If you want to get a decimal approximation, use a calculator, and your calculator knows that e is approximately 2.7, and figure the decimal approximation out. Another example, now we have 3 curves and we want to find the area between 3 curves. First one is x plus y equals 4. So that doesn't really look very good to me, so I'm going to write it as f of x equals, I can write it as f of x is equal to y is equal to 4 minus x. Then the next function again, it's not written in the function form, it's written in the equation form, and I can get g of x, which is same thing as y, equal to x. And then last one, I can isolate the y again, that would be negative 3x plus 4. Negative 3x plus 4. So we have f of x, g of x, and h of x. Here we graphed f of x, g of x, and h of x. And again, the issue here is we need to find where do the curves intersect. So intersection of curve f of x and g of x. Where do the f of x and g of x intersect? F of x is 4 minus x, g of x is x. So I get x is equal, this gives me x is equal to 2. So at x equals 2, my f of x and g of x intersect at x equals 2. When x is 2, what is the y coordinate? So we can figure out 2 comma, we can plug 2 into either f of x or g of x. If I plug 2 in there, I get the y value as 2 as well. So f of x and g of x intersect at 2, 2. This point is 2, 2. And intersection of curves g of x and h of x. G of x and h of x. G of x is, let's see, the g of x curve is x. H of x is negative 3x plus 4. So that leaves me with 4x is equal to 4, x equals 1. So my point of intersection for g of x and h of x would be, if I plug 1 back in, I get the y as 1 as well. So this point is 1, 1. Now I'm looking for intersection of f and g, g and h and f. Intersection of f of x and h of x. We're going to plug them equal. 4 minus x equals h of x is negative 3 plus 4. So that leaves me with 2x equals 8. And let's see, I would add 3 over here, so that would give me 2x equals 0 and x equals 0. If I plug x as 0 in either f of x or h of x, y comes out to be 4. So here's my points of intersection, and I'm ready to set up my integrals. I will have to separate two integrals because in half of the curve, f of x is on the top and h of x is on the bottom, and other half of the curve, other half of the graph, f of x is on the top and g of x is in the bottom. And I will split them from 0 to 1 and then 1 to 2. Okay, so from 0 to 1, which curve is on the top? F of x is on the top. F of x was 4 minus x, minus h of x is on the bottom, which is negative 3x plus 4. And then from 1 to 2, x equals 1 to x equals 2, I do have f of x on the numerator, which is f of x is 4 minus x. And the bottom curve is g of x minus x dx. Now, one thing that's really important to keep in mind when you distribute the negative, don't forget to change the signs if you have a binomial or a trinomial that you're subtracting. Okay, I'm going to clean it up a little bit, and I might not finish it to get the final answer because the rest will be all calculator work. So between 0 to 1, I would have, let's see, from 0 to 1, 0 to 1, 4 minus x, and it would make a plus 3 minus 4. So 4 minus 4 is just going to be 0, and 3x minus x is 2x dx. And then between 1 to 2, 4 minus 2x dx. So again, at this point, use the calculator, or this is pretty simple without a calculator as well. When we perform the integration here, it turns out to be 4x minus 2x squared over 2 between 1 to 2. If I plug a 1 in here, and I can just get rid of the 2 and 2. So that's just going to be 1 here, and 1 plus, if I plug a 2 in there, 4 times 2 is 8. 8 minus 4, which is 4 minus, if I plug a 1, 4 minus 1. 4 minus 3 is 2. Let's check here. I think I did rush, so just figure out the definite integral here. I'm running out of the space as well. So that would be 1 minus 0 for this one. And 4 times 2 minus 2 squared is 4, minus 4 times 1 minus 1 squared is 1. So that leaves me with 1 plus 8 minus 4 minus 4 minus 3 is 4 minus 1 is 3. So 8 minus 7 is 1, and 1 plus 1 will be 2. So 2 is the area between these two curves, okay? 2 is the area between these two curves. Let's check out, what if we are given x as a function of y? What if I'm not given y as a function of x, but x is a function of y? So I have g of x equal to some, f of y equal to, so my functions will be given in terms of y. I wouldn't have the y by itself, but I would have x by itself on one side. In that case, the functions, we'll have to think about which one is the right curve, which one is the left curve, and the bounds c and d will be the y values, and we'd be performing integration with respect to y. So we'll go with the right curve minus the left curve, and c and d are the points of intersection of those two curves, but they're going to be the y values in this case, wherever they meet. And then we need to think about the right curve minus the left curve, and that would give me the area between those two curves. All right, let's check out first example. Find the area enclosed to the right of y, x equals y squared minus 5. So we're given x as a function of y in both cases. So let's see. First thing I'm going to do the graph. So graph the f of y and g of y. Both are parabolas. One is facing, if y is negative, that's going to be facing to the left. If y square is positive, it's going to be facing to the right. And now find the points of intersection. Points of intersection of points of intersection would be set the two curves equal to each other, because they both are equal to x, so they both are going to equal. So this gives me 2y squared equals 8, y squared equals 4, y is equal to plus minus 2. So this has a y value positive 2, y value negative 2. We don't need to find the x coordinates. We really just need to find out the y coordinates. That's all we need for the integration. So no need to find the x coordinates. If you want, you can, but this is positive 2 and this is negative 2. We just need the y values for integration. So going from negative 2 to positive 2, the right curve, the curve on the right, because we want the area in between, you're going to do the right curve minus the left curve. The right curve in this case is g of y. Again, this is going to come from the graph. If you don't want to graph, you can plug different x values and see different y values and see which one gives you a bigger x value. The one that gives you a bigger x value is your right curve. So this is your f of y, g of y. So that's going to leave me with 3 minus y squared minus 5y squared minus 5 dy. Now we're going to be integrating with respect to y. 3 minus y squared plus 5 dy. Seems like the y squares are staying. So negative 2 to 3. And 3 plus 5 is 8 minus 2y squared. Now let's go ahead and perform the integration and then apply the bounds. 8y minus 2y to the third power divided by 3. We are going from negative 2 to 3, the bounds. So complete the definite integral. Use a calculator to find the definite integral. I will just leave it at this point, or go ahead and use a calculator. So we have definite integral. The lower bound is, my calculator doesn't have y, so I'm just going to plug in terms of x. It doesn't really matter. It's going to give me the same solution. So we have 8x minus 2/3 x to the third power. If you want to be more exact, leave your answer in terms of fraction, unless you are being asked to give a decimal approximation. 55 over 6. Let's see if that is... okay. My bad. Messed up. I somehow changed that 2 to 3. The upper bound was 2. So fix that, please. The upper bound was 2, not 3. That's going to be 2. Okay, so now change the upper bounds in the calculator. Leaves me with 2. That is negative 2 to 2. 8y minus 2/3 y to the third power. Let's see. I'm going to add a space here. Okay. So 3 minus y squared. Alright, so let's plug the positive 2. 8y minus 2/3 y to the third power. And we're going from negative 2 to 2. 8 times 2 minus 2/3 2 to the third power minus 8 times negative 2 minus 2/3 negative 2 to the third power. 16 minus 2/3 times 8 minus negative 16, and this is going to become positive. 2 to the third power is 8 times 2 is 16 over 3. Okay, so 16 minus 16 over 3 plus 16 minus 16 over 3. That does not look right. So negative times negative is a positive, and then we have positive. Negative 16 over 3. Oh, okay. So this is going to leave me with 32 minus 16 over 3 minus 16 over 3. And I can combine these like terms. 16 and 16 gives me 32. And now we can write it as 3 in the denominator. And 32 times 3 is 32 times 3. 96 minus 32 turns out to be 64 over 3. So that's the area between these two curves. Remember, keep in mind, first thing you want to identify if you're given y as a function of x or x as a function of y, that is going to decide your bounds of integration. That's also going to decide if you're going to integrate with respect to x or with respect to y. Another example, again, we are given y as a function of x. So I can say f of y here. So any function you can call f of y or g of y, or you just need to know which one is the right curve, which one is the left curve. So in this case, my right curve is x minus 1, and left curve is, I use Desmos to make all these graphs. So take help of Desmos if you don't want to spend too much time on graphing. You should know how to graph these. These were all covered in pre-calculus in college algebra course. So here we are. We're going to do right curve minus the left curve and perform the integration by finding the points of intersection. So y is equal to x minus 1, y squared is equal to 2x plus 6. So how do we find the points of intersection? What we can do here is I can write both of these because because I have a horizontal parabola here. I can write them as x is equal to y plus 1, and I can write x is equal to y squared minus 6 divided by 2. Y squared minus 6 divided by 2. Okay, so now we can set them equal to each other. Y plus 1 equals y squared minus 6 divided by 2. That's 2y plus 1 is equal to y squared minus 6, y squared minus 2y, and then we have minus y squared minus 2y minus, this would be a 2. Y squared minus 2y minus 8 equal to 0. When I factor y minus 4, y plus 2 is 0. So I get y as negative 2 and positive 4. So my 2 points of intersection are y as positive 4 and y as negative 2. That's all we need. We just need the bounds of integration. Now I'm ready to plug it in. Right curve minus the left curve, going from negative 2 to 4. Right curve is x minus 1, and the left curve is 2x plus 6. X minus 1. Nope, I am writing them as functions of, we are writing them as x as function of y, x as a function of y, because it was easier to isolate the x's from here. I couldn't make the y's equal because one was y and the other one y squared. So I'm going to be using where I isolated them. So the right curve is y is equal to x minus 1, which would be x equals y plus 1. Y plus 1 minus the other curve is y squared minus 6 over 2 dy. Go ahead and evaluate this integral using a calculator. I'm going to stop it at this point. Next example, find the area enclosed by y is equal to natural log of x over x and y is equal to natural log of x squared over x. So very first thing, we want to find the points of intersection. How do we find points of intersection? One thing we know that we are given y as a function of x, so we're going to be looking at the top curve and the bottom curve here. To find the points, natural log of x over x equals natural log of x squared over x. So what we can do is we can bring everything on one side and bring 0 on the other side. Now I can pull out a natural log of x over x, and inside I'll have 1 minus natural log of x. Now when I do the 0 product property, then product of two functions is 0, or product of two terms is 0. One of them must be 0. Either 1 minus natural log of x should be 0, or natural log of x over x should be 0. So this leaves me with 1 is equal to natural log of x. If natural log of x is 1, x is equal to what? What is x going to be? If natural log of x is 1, x would be e. If natural log of x over x is 0, that means natural log of x is 0. And when is natural log of x 0? When x is equal to 1. So my bounds of intersection are 1 and e, and I don't need to find the y value there. I'm ready to set up the integral. I need the top curve minus the bottom curve. So top curve is natural log of x over x minus the bottom curve is natural log of x squared over x dx, and we'll be performing the integration from 1 to e. E is about 2.7, so e is bigger. E will be the upper bound. Now, how do we perform this integration? How do we do the integration of natural log of x over x? We will have to do u substitution here. We can call the u as natural log of x, then 1 over x dx will be du, right? So we can do the u substitution. Let 1 to e natural log of x over x dx minus 1 to e natural log of x squared over x dx. Let me add a page and complete this integral here. 1 to e natural log of x over x dx. 1 to e natural log of x over x dx. And then we had minus 1 to e natural log of x squared over x dx. So we can do this one first, and I'm going to just try to use different colors. Let natural log of x as u, 1 over x dx would be du.